I can go count to 15. So 15 is 1, 1, 1, 1, 1 in unsigned. So when I write problems, I can test or in homework, we'll say 4-bit unsigned binary number. And so you know how many bits you have to do your arithmetic. So this is for 4 bits, I can represent 15 numbers in binary with 4 bits. So in sign, we taught the first way. So sign magnitude, what we do to get negative numbers using sign magnitude? 1. Yeah. So my bad.
Yeah, I'm just like,
My bad. You actually told me about that.
that's weird.
Alright. Trying to do it fast. Alright. So all we did was we just took the most significant bit and we just made that our sign bit. So 0 is positive, and then all we did was switch the most significant bit to 1 to be negative. So we got -1, -2, -3 with just putting the 1 in front. So you can see -7 is the same as 7, just that the last bit has a negative sign. I showed earlier that we couldn't do arithmetic with sign magnitude, so we needed to do something different. So we did was 1's complement. What do we do to get 1's complement?
Switch the bit.
Yeah, so we did the same thing. We had to make a sign bit, so we kept the sign bit. But all we did was we said we flipped the bits to, there were zeros, now they're 1s, and 1s to zeros, and they put the 1 in front. So if we had, I'm going to do -7 is 1, 0, 0, and 7, positive 7 was 0, 1, 1. So we flipped the last 3 bits, added, changed it to negative sign, done the significant bit to 1, so that we get the -7 on that one. But I didn't quite finish. I did somewhat a fib, because we did -3, right? And +3 last time. Yeah. And we got 0. We got 1, 1, 1, 1, which we got -0.
That would be positive 0.
No, it's -0.
Oh. Well, I thought after you were done with it, you switch all the bits again.
No. No, we just keep it like this. But one person brought up at the end of the class. I'm going to do number 2. I'm going to do 2. 0, 0, 1, 0. So that's number 2. That's 2. And I'm going to do -1. 1, 1, 1, 0, 1.
To get
What? That's 3 1s.
0, 1.
0. Right there. So I'm going to get 0. I get 0, carry the 1. Do that. 0, carry the 1, 1, 0.
Oops.
Yeah. You got 0. Should equal to what? 1?
Yeah, should be 1.
So this doesn't work. Right? Some of our arithmetic works, some of it doesn't work. Right? So we have to come up with another one. Hopefully you can see, what do we need to do to this one? Just need to add 1. So if we just add 1 to all these negative numbers, we can do arithmetic. So we call this 2's complement. This is what we standardly use in computers. It's the way everybody tests. Basically, all we want to do on sign magnitude 1's complement is you just know the difference to and disadvantages of each one. All right? So basically, what's the disadvantage of 1's complement?
2 zeros.
You can't do all your arithmetic, but you can do, minus itself. we get 0. One's complement, you represent the number, but you can't do any math. And 2's, we can do everything with it. So, this is how we.
What'd you say the advantage of ones was again?
Advantage of 1 is that we can do some math. I can do -3 minus 3, and I do get 0. So I can do some math, but it's not. I can't do -2 minus 1, basically.
You can.
So, and so we're going to do a little trick here too. So we're going to get rid of this redundant 0 as well. So I'm not going to have an extra 0. There's no point of having that wasted bit. So we have to create a whole new system numbering, which is still the same for positive numbers. I still get the same amount of positive numbers. So we're going to go change it from, I'm going to go -1, -2, 3, 4, 6, 7. So I get one more. I only have -7 here. I get -8 on the negative numbers. And all the positive numbers are all the same. So that's all the same. So I'm going to do -1. So this is how we do 2's complement arithmetic. So I want to make -1. So I'm going to take 1, 0, 0, 0, 1, and then we're going to do the flip the bits again. Get 1, 1, 1, 0. Now I have to flip. Then we're going to add 1 to it. So I'm going to add 1. So now we get 1, 1, 1, 1. So in 2's complement, 1, 1, 1, 1, 1 is -1.
Should be 1.
It should be 1. Okay. So, what should 2 be? Yeah, 1, 1. I'm just gonna skip to flipping them. 0, 1. We add 1. So we're gonna get 0, 1, 1, 1. That's gonna be -2. Alright.
It looks exactly like one's complement.
Yeah. The only difference is we're just adding 1 to, basically, since this is -1 here, we're adding 1 to this, 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 1 to this. That's all we're doing.
What's 0 then?
Well, 0's already here. 0's up here. So
Zero.
look at these numbers here in this column for this set, because we're gonna have, like I said, we decided we want to get rid of this -0 that we've been doing for 1's and 2's. One's in sign magnitude, so that way we can get an extra digit. And
So I guess I don't understand the difference between one's complement and two's complement.
let me finish the table,
Okay.
and then I'll do the math. Basically, you'll see what I can do math.
Yay.
We're gonna start from the bottom up. That's the way to do it.
Yeah, that's right.
But, okay, that way.
Yeah, that's right.
Yeah, okay. So, now, I'll do, arithmetic here. So, I'm gonna take -2, I'm gonna take, well, let's do 5. I like 5. 5 is an easy binary number to remember, 0, 1, 0. And we'll subtract 2, so, or add 2, I want to say. Negative. So basically say, hopefully you know that it's like doing 5 plus -2, which is in essence 5 minus 2. So we go 1, 1, 0, carry the 1. We get 0. Get another carry. Since we're working in 4 bits,
Ignore it.
we throw it away. It's gone. We ignore it. And so what do we get?
You get 3.
We get 3. And that's my math, right? So we get 3. So now we can see that with 2 complement, I can do any math, right? The 1's complement, I can only do like 5 minus -5. I couldn't go 3 minus -2. I couldn't get the right number. Yeah.
Can I ask you to do like 5 minus 5? 5
Yeah.
and then -5?
Yeah. So if I go 0, 0, 1, 0, 0, 1, 0, and go on -5.
Negative 5 is 1, 0, 1, 1.
-5, yeah. 1. Right. Yeah. So I get 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1. Ignore that, I get 0. Alright. Okay. So, that's on those ones. So what if I do this? I'm going to do 5 plus 5. Okay. We're going to get 0, carry the 1, get 1. Get 1 plus 1, we get 0, carry the 1, get 1. That's what, -6?
Don't have enough bits.
I don't have enough bits. We call this overflow. Alright? So definition of overflow is when adding 2 positive numbers are negative, basically 2 positive are negative values. Okay, so when I add 2 positive values together and get a negative number value, overflow occurred. If I add 2 negative values together and get a positive value, overflow occurred. Right? So if I do the same thing, if I do -5, we get 0, carry the 1. So 1 plus 1 plus 1. For every root of 6, we get 1, carry the 1. Okay, get 1. Get 1 plus 1, I get 0, carry the 1. We ignore it, so that means we get
Six.
6. Right, which would be exactly that. So here we can say, in your problems, you say overflow. You know, that's happened. So see that if I do two negative numbers, get a positive number, overflows occurred. If I add two positive numbers together and I get a negative number, I get
Now, how do you
Overflow.
determine if that first one is negative? Why wouldn't it just be 10?
which one?
The negative 6.
Negative 6. If I explicitly say 4 bits, like
Okay.
we're all working 4 bits here. See, if I had 5 bits, I can do 10.
Right.
Um,
Well, no, but what I mean is, because
Yeah.
up there I see 2 plus 8, right?
Which one? This one?
Yeah. Right, I don't see the negative 6. Like, how do you determine if it's negative 6 rather than 8?
He's working in sign,
Or-
so the first
Yeah.
one.
So yeah, if you want to say is I
Yeah,
should.
that would do it, yeah.
If I do, this is probably the best way to say it.
Okay.
So-
That makes more sense to me.
Yeah. Sorry. I try to stay color coordinated, but I keep having to flip markers, so. Same with this one is these, let's draw a line down the line. So these are my sign. As I do the addition, we treat the sign bit as addition as well. So that's what happens with that. So, any other questions on that sign magnitude?
But if you add like -3 and -3, you should be fine, right?
Yeah, if I do -3, I should get -6. We'll have plenty. I'll do that one right now. So we get 1, 1, 0, 1, 1, 1, 0, 1. We get 0, carry the 1, 1. Plus 1, 0, carry the 1. 1 plus 1 is 1. Carry the 1. Ignore it. We get -6.
That worked because you stayed within the,
Yeah, I stay within my limits on the 4 bits,
yeah.
right? So it's one of those ones where like, I'll have problems 8 bits, 9 bits, 5 bits. And so you just have to know how many bits you can represent. So best way to do is know how many bits you need to represent is somebody say, okay, I have 2 to the 4, so that gives me 16 unique values, right? What I know is that if I divide it by half, I get 8 for you sign. But the count for 0, so I'm going to get 0 to 7 for positive values, and negative, we're going to get -1 to -8. Okay. If I do 2 to the 5th, that is 24, right?
32. 32.
Yeah. That's better. So divide it by 2. What's our range? So yeah,
15.
it's 16. So we have to go
0
0 to 5. And
15.
then we get -1 through 16, -16. So that's our positive negative range. So this is a way to, you can also see what you can, really big binary numbers. This is probably the easiest way to tell what's your largest negative number you get, what's the largest positive number you can get by doing this.
When you're working with sign magnitude, don't you have to
Well, sign magnitude,
take one of the bits out?
yeah,
So
basically.
you have 3 instead of 4 and 4 instead
Yeah,
of
if I was doing sign magnitude, it would be, I would have 0 through 15 here, I would have -0 through -15 on sign magnitude. Because both of them will have a positive 0 and a negative 0. But we don't need to worry about doing anything. all I'm gonna really test on is what's the difference between these three, when I'm talking about this one. Like, what's the advantage of sine magnitude versus 2's complement?
Can you go over that real quick?
Ryan, I have a question. I have a question first.
Okay.
How can you look at a number? I can look at the positive number and figure out what it is
Mhm.
by looking at it. How can you do that with a negative number, though?
Do the same thing. I didn't do, if I go -5, if I want to make this a positive 5, we do the exact same thing as we did 2's complement. So we're going to flip the bits. So we're going to go 0, 1, 0, 0. And then we're going to add 1 to it. So now we're going to 0, 1, 0, 1. You see that is a -5. So we flip the bits. We added our 1. So now I see that I got a 5.
So you have to do that process in your head to figure out what, if you were just looking at a number, you didn't
Yeah,
have all the
yeah.
nice table.
The only thing is, like, the only way you can tell if, you always assume unsigned unless it says signed. So you, for the last bit. So sometimes this might be, actually be 11. It could be 11 and unsigned. And so, it depends on what you specifically say. You know, just
Well,
like,
just working within the environment that you're showing there, that's what I was
Yeah.
concerned about.
if I'm doing signed 4-bit numbers,
Right.
that's what we do. So same thing if I did 6 numbers, all we do is we add the zeros in front here, which this would be, let me do that first. Okay. Let me ask your question first.
Yeah.
What's the difference? Let me answer this question, and then go yours. So what's the difference between sine magnitude and 2's complement? Is one, we reduce, we get rid of the -0.
Right.
So we get an extra digit to do arithmetic, and in 2's complement, we can actually do the arithmetic. We can do the whole full range of arithmetic. We can do division, multiplication, subtraction, all that stuff.
So is there any advantages using 2's complement over 1's complement other than being able to, what was it, add negative numbers?
Yeah. So that's basically that's the difference. Pretty good. Yeah.
With 4 bits, can you do arithmetic with the number -8? Because it's -0, 0.
I can add 5 to it.
And it would come out right.
Yeah.
Really?
Yeah. If I go, so 1, 0, 0, 0, and I add 0, 1, 0, 1. So I'm going to get 1, 0, 1, 1. So this is -8. This is 5. We get 3.
Oh, okay.
So whenever you add two opposing signs, it'll always work out. But if you add two
Mhm.
of the same sign,
Yeah.
it most likely will overflow.
Yeah. As I said, if let's say if a -8 is -5, it's fine. As a do example, you can always do the math. But when you have both negative and positive signs, you have to look for that overflow error that would happen. And so in your problems, when you have the overflow happen, make sure you specify overflow happened, right? Because it's wrong. And so I don't want to see -5 plus -5 equals -6. So unless I said, unless I go, there's some problem might be, you have infinite amount of bits. If you have infinite amount of bits, you let the carry go through and drop the carry down. And so that can, another example. Okay. Okay. Next thing is called sign extension. Right. Let's say I'm going to have a 3-bit number here. So I'm going to have 0, 1, 0. So hopefully you know now that's 2. And this is my sign bit. I'll keep the color going for you guys. another number, say, let's go with that 4-bit. I got So I want to add this 4-bit number to that 3-bit number. So what we do is called sign extend. So you know this is a positive number. So all we have to do is, what we do is, I'm going to take we got 5 here. So I'm going to take 2. And all we do is add the 0 in front of this, sign extend it, right? This is for positive numbers. So when I do the arithmetic, I get 1, 1, 1, 7, 0 out front, right? So we get that as correct, because we want to do that. If I want to do negative numbers, so if I do -2, 1 out front here, I'm going to use the same 4-bit 5. So what we do in this case, -2, we sign extend the -1 over that way, right? So in positive number, when we sign extend, we add the 0 over. In negative, we do ones all the way over in sign extend. So if I do the math here, 1, 1, 0, 0, 1, we get. So, everyone see that, how to sign extend? I think simply need another example on that. So, like I said,
So if you had like an 8-bit, you would extend the ones at the 8 bits.
yeah. If I wanted, yeah, then I just keep adding ones here, all the way out this way. Keep adding zeros out here. Basically, as far as I need to go to do, if I change this to whatever bits I need, whatever my larger one is, we go with that. I need to sign extend the lesser one out to equal the same size. Right? Good. I believe the book did, and page 24 did more numbers, but you can make this table as big as you want. So. Alright. Then we're going to talk about some logic operations that we can do. The first one is and, or if you do like C coding, double and symbol. In Word, it means the output is 1 only if all inputs have 1. Right? So I'm going to draw what's called a truth table. So this is going to be input, and I have output. And we're going to define A, B, and this is my output here. So I have 0, 0. When I'm ANDing, I'm going to get 0. Okay? 0 to 0 is 0. 0, 1 is also 0. I'm going to AND. So about 1, 0. I'm going to add 0. Yep. 0 again. And 1, 1 is
1.
1. Yeah. So output. Yeah. Output is 1 only if all inputs are 1. So if I have my 2 inputs, 1, 1 is the only one that gets 1. Right. So this is the truth table for it. So I was doing the operation. So if I take this number and this, some random bits. So we're going to AND this together. 1 and 1 is
1.
0. Right. 1 and 1 is 0. 1 and 1 is 1. 0 and 0 is 0. So this is the ANDing operation of adding these two numbers together. Alright, next one is OR. We've got programming double bar. It's defined as is 1 if any input is 1. Right? So if I go to the truth table again, so I'm going to OR A and B together. Both of them are 0.
0.
0. I'm going to
One.
OR 0 and 1.
1.
1. Right? Because one of the inputs is 1. So our output is 1. 1, 0.
1.
1. And 1, 1 is 1. Okay. So if I do this same operation, but I OR it instead, I'm going to write the word OR. Bars start looking like 1s. So if I do this operation, so 1 OR with 1, 0, 1, 1,
1,
0 with 1,
0.
1.
1.
Okay.
Yeah. And then this is 0. Okay. So that's the OR operation. Okay. And the last one is not. The output is 1. Let's see. The new definition is the input is 1. Output is 0. Input is 0. Output is 1. this only works on one variable, one input. So if I have a 0, I get a 1, I have inputs of 1, I output a 0. Okay? So if I take 5, which hopefully, if you remember we did
Flipping it.
yeah, just flipping the bits. So if I'm not, just gonna not this, I get 1, 0. So that's the non-operation. Any questions on those operations?
When we use those operations in high-level programming, that's what's going on.
Yeah, they're still doing the, they're
flipping.
they're actually flip bits. So if you did an int, you had an int,
Right.
you knotted it, so if you did the, it's a little squiggly line, like that sign, in front of it, like this is x, you hit the knot in front of the x, this would flip the bits.
That's in C, they do the caret.
Yeah, I was gonna say in C, you do that carrot.
So I know in Java they do the exclamation mark.
Yeah. To do it this way or do it that way?
That
They
way.
put it in front.
Yeah.
Isn't C++ also?
I think you can do both ways. Yeah, I think you can do both in C sharp, in C ++. Or maybe in some C you can do, depending on if it's ANSI C or just regular C. You can do that. So that's what, they're doing the same kind of operation on those ones. Any other questions?
So it's not just flip the bits, is that?
Yeah, go ask me that. Not just flip the bits. Like and or, we had to have 2 inputs to do the, you can't and one number. You know, you have to have 2 numbers, 2 things to and not not one of the input.
Can you do with the and the or 3?
Yeah, I can add 3 together. It's the same thing. So if I had 0, 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, and if we did the AND operation, so I have 3 inputs instead of 2 inputs I do in the example, but it's the same thing. I wrote the definition. So definition was all inputs have to be 1, right? So all these are 0, so and this goes to 0. One of these is 0, so this is 0. 2 are 0, so I get a 0. And then same with that one, so I got zeros. So when I add these 3 numbers together, I get 0. Why not?
I don't get that.
Because the definition is all my inputs have to be 1, and my output is 1. Right? If I have a 0 in any inputs, it's 0, according to the definition. So I have a 0. When I'm adding 0, and it with 0 is, you want to say that is, you can also split it up this way. So adding 0 to 0 is 0. And you add 0 to 0.
And is kind of like multiplying, because if you have everything as 1, 1 times 1 is 1. But if you put a 0 anywhere in it, then it's going to be 0.
Nah. It makes you feel good with that. Nah.
Just show an example where the answer has a 1 in.
Yeah. So
Before you do, if you were to do an AND, that first one would be a 1, right?
if I did an and,
Not AND. Does that make sense?
let's wait a semester. Debate a couple weeks, okay?
Alright.
All right.
Oh, okay, never mind. We were doing an and. I thought
Yeah.
we were doing a not.
Yeah. Sorry.
Check.
Okay.
Alright, never
We're good.
mind.
We're gonna do nanding later. Okay. Just not right now. In chapter 3, we're gonna do some more logic. I'm just introducing these ones. Okay. Yeah.
That same one, can you do it more?
Yeah. So if I do, so now I'm gonna switch it. So I'm gonna get rid of these lines here. So we're gonna do the or now. So oring is definition was.
Either
One of
It's
the
a
bits is
1.
1.
Yeah, so if there's a 1, the output's a 1, no matter how many ones there are. So 0, 0, and 0, so 0 OR with 0, OR with 0 is still 0. Okay. I have 1 OR with 0, which is 1. I have 1 OR with 1 is a 1. We get a 1. And then you got 0 ORed with 1, which is 1. You have 1 ORed with 0, which is still 1, so you get 1. And ORed with 1, 1. You got 1 ORed with 1, so it's another 1. So that's my ORing operation now. Okay. To me, the quick way is to see I'm doing ORing. Oh, 0, get a 1. Oh, the 1 in there, 1. The 1 in there is 1. The 1 in there is 1. Same way with ANDing. I have all 1s, so I know it's a 1. Other than if I have a 0 in my input, I always know it's a 0. If there's a 0 in my ANDing, yeah.
I wanted, thank you for laying this to true or false.
Yeah.
Is that, I guess that's.
Yeah,
the logic.
you want to say,
So
basically,
if one of the inputs is true,
mhm,
or the other one is true, then it's true.
yeah. So ANDing is, everything has to be true to be true. Or is, only one thing has to be true to be true. Right? So if they're all false, it's false on both cases. So that's a better way to say it. So we have, you want to say, this one is true, this is true, because that's true, that one's true. And they have 2 truths, but it's still true no matter what, so it's true. And you have 2, all 3 are false, so it's false. In the ORing. Or you want to think light switches. If you have one switch that's on, the light's on. Same way, if you have 2 switches that are on, light's still on. All are off, the light is off.
So what would a not look like?
A not, I only do one variable for not. So if I was knotting it, I just take that number and then just flip the bits. So 1, 1, 0, 1 for that. If I not, that number there equals that. Basically, it's like, if I was false, now I'm true. If I was true, now I'm false. Like, I was on, now I'm off. If I was light switch. Okay, I don't have much time to do this, so we're going to start it. So I'm probably going to review it again Friday. So now we can convert binary to decimal. So if you remember, when we did 321, I'm going to put 10 underneath here. So this is a decimal number, 321. Remember we did 3 times 10 to the second power, let's say 2 times 10 to the first power plus 2 times 10 to the 0th power.
It should be 1 times 10 to the 0, right?
But yeah. So basically is, we're in base 10, so this is the base, and you want to say this is the position. So this is in the 2's place, this is in the 1's place, this is in the 0's place. And so we do that. The same is with the binary. So if I have 0, 1, 0, 1, okay? Remember your table, we already knew that was 5, but we're going to do it this way. So I got 0 times 2, I want to say this is the 0's place, this is the 1s, 2s, 3s. So this is my base, for base 2 for binary. So then I can just go 2 to the 3, sorry, yeah, plus 1 times 2 to the second, plus 1 times 2 to the 0. Okay. 0 to the 1 plus 1 times 2 to the 0. Okay. 2 to the 0 is 1, so 1 times 1 is 1. 0 times 2 to the first, which would be 2. 2 times 0 is 0. 2 times 2 to the second power is 4. 4 times 1 is 4. 2 to the third,
8.
8. 8 times 0 is 0. 0 plus 4 plus 0 plus 1. Right? So here I just converted this binary number to decimal. So
Can you do 1 0 0 0?
I have 1 0 0 0.
Yeah, and that's signed.
Okay, it's signed. Okay, this is unsigned. If you want to say.
Oh, okay.
It works the same way. What we have to do is this. So this is, you didn't do sign right here, right?
Yes.
Okay. So we have to convert it over first. So we're gonna have to flip the bits. Add 1. So we're gonna get 0, 0, 0, 1. Oops, that's the number.
0.
No.
It's -8. That's why I was wondering if you could do that with the -8. Because there's no translation into positive.
Not enough bits.
Not enough bits. Yeah, so I can't do -8. Sorry.
I was wondering about that.
Yeah, so I can't do -8. But if I was doing, let's do -1. So I have -1, so we flip the bits, add 1 to it, so now I get 0, 1. So I get 1. Now the only thing you have to remember is now that instead of, right here we have +5, so now we're just, our result's gonna be negative, because we knew that our sign bit, let me make sure I can do this for you. So we knew our sign bit in the beginning was negative, so we just have to always know that we did a negative number. So
Why are we adding,
what?
why are we adding these?
We're doing 2's complement. We're always doing 2's complement. Like from now on, everything's gonna be 2's complement. Right? We just kind of showed why we do 2's complement versus other forms of making negative numbers. What I want to say is, I'm doing 2's complement on all my numbers are always going to be 2's complement. And so hopefully you just look at the math. I can just have 1 times 10 to the 0th power, so it's going to be 1. But I knew my number was negative, so I know it's -1. It's I'm doing the binary to decimal, right? Okay, that's it for today. We'll do decimal to binary on Wednesday.